Let me take you through a fictitious case demo involving Kissan Jams, a famous FMCG confectionery brand in India. We will model its supply chain, also known as supply chain network design. This supply chain is a typical of a three-echelon supply chain, the three nodes being the supplier, which is the farmer, manufacturer, which is Kissan Jams, and distributors. Initially, I will give you an overview of how the baseline model has been developed and which flows we will derive. Subsequently, I'll take you through the results and add in another constraint pertaining to controlling the greenhouse gas emissions, specifically the carbon dioxide emissions related to inbound and outbound transportation. Let me take you through the unsolved baseline model first. What we are trying to derive is the lowest total supply chain cost. It is a function of the inbound transportation cost, that is the logistics cost of the product flows between the farm and the manufacturer. The outbound transportation cost, which is the same but involves the manufacturer and its customer, the distributors, as well as the cost of manufacturing operations, which is both the fixed as well as the variable operating costs. Kissan Jams has two suppliers, a farm in Ranchi and a farm in Nashik. They both can supply to 4 plants of Kissan: Jaipur, Pune, Cuttack and Mangalore respectively. Both these farms produce a sum total of 50,000 pallets of agri-produce annually. This is how a pallet looks like. And we have to basically determine how much quantity will be outflowed to which of these factories of Kissan Jam. And to support us, there is data available such as inbound transportation cost per lane. So Ranchi to Jaipur, for example, costs 525 rupees per pallet, and so on and so forth. Similarly, we have outbound transportation cost involving the flows between the Kissan Jam and its distributors. So we also have to determine whether we need to locate all the 4 factories or can the work be done in 3 factories also, because we are optimally solving the problem statement. Beyond that, we also have to determine the flows from the factory and which distributors it will service. So will Jaipur service Pune, or will Cuttack be best positioned to service Pune, and so on. So besides the outbound transportation cost, the most important aspect is the annual product demand. So you can see the sum total is 45,000, and you knew that the suppliers can supply 50,000. So the suppliers are in a position to completely fulfill the demand also. One more decision that we need to take is what is the capacity of each of these plants. So there are 3 configurations: 10,000 units, 20,000 and 30,000 units, and as well as the fixed cost associated with it, as well as the variable cost, which is like the handling cost and the other charges which are variable to the number of production. So at the top of the screen are the 4 variables, and basically those are linked to the Excel sheet, and therefore we are now in a position to solve and find out what are the numbers that can be filled up in the yellow cells, which will ultimately give us the optimal total supply chain cost in the green cell. Such problems can be solved in Excel's inbuilt linear programming tool, the solver engine. We first have to set the objective function, which is our total supply chain cost, and we are minimizing it. So we'll set that. Subsequently, how we'll derive that is by changing the yellow shaded cells, which are our decision variable cells. So which is the farm to factory flows, whether the factory is activated or not, the factory to distributor flows, the factory production capacity, and so on. So these are our variable cells, and the constraints are very important. These are basically the parameters which basically restrict the model or allows it to flourish in a particular direction, a particular trajectory. So for example, there are certain binary constraints. We want a particular plant to supply a particular distributor, either yes or no. So we will get that answer in these yellow shaded cells, and which is why we encode it as binary. Then some cells we want it as integer because we don't want decimal places. We don't want to ship 1.5 pallets. We can ship 1 pallet or 2 pallets of produce. Similarly, there are other variables as well. For example, the units shipped to distributor should not exceed what the plant is capable of producing also. Likewise, I will not explain each and every one of these integers, but the model has been built so that the answer is optimal and several practical constraints are taken care of. So for example, we don't want integer can assume a negative figure. So we don't want the factory flows from the farm to be in a negative number. So we also encode that. I had solved the model previously and derived the feasible solution. Let me take you through it. The total supply chain cost has been optimized to 4.64 crores, whereas notice this figure, inbound plus outbound transport is 2.9 crore roughly. The fixed plus variable factory cost is 1.8 crore roughly. The weighted average distance each pallet travels is 440 kilometers. The farm to factory flows, you can see that out of the 50,000 capacity, because the demand is 45,000, 30,000 has been transported from Ranchi, and 15,000, which is completely capacity, Nasik will be supplying to some of the plant as per the configuration. In terms of which plant will be active, as you had already observed, all the plants have been active, which is not a surprise if you think the geographic, you can say, dimensions of India. In terms of the factory to distributor flows, Jaipur will obviously supply to Jaipur because it is in the same location and the cost is zero, technically speaking. And Srinagar, for example, let me take you through it. So if I scroll to the right, the Srinagar, the total transportation cost is 18 lakh rupees. How has it been derived? It is basically 750 is the cost which Jaipur will undertake, and 2,400 is the annual demand. So multiplying both, you get the 18 lakh of cost, and similarly other configuration also has been calculated accordingly. In terms of the production capacity, Pune and Mangalore will operate at the lowest production configuration, which is 10,000 capacity, whereas the other two will operate at the mid. But the point to note is, because all the factories are active, they have to choose one configuration. And despite they may have the larger capacity, they will eventually only ship the demand, which is the 45,000 units to the distributors. So overall, you can understand the nuances of the model, how the parameters lead the model to a particular solution. And if one can alter the costs, amend the cost, there are revisions, then the model will also change considerably. Each of the cells are also encoded. So for example, the inbound as well as the outbound transportation cost are linked to the model, because otherwise the solver will not compute that result. So each of them are linked, and this is how we basically, the model has optimized for the lowest total supply chain cost, which is the sum of A1 to A4 cells basically. So this is 440 kilometers is basically the weighted average outbound distance flows. Now we'll add the constraint, which is the crux of this demo, which is the reducing emissions, reducing the greenhouse gases arising from the inbound and outbound transportation. So we had added several constraints, but we had not factored in the carbon dioxide which is emitted from the transportation. So we have that data for both the farm to factory flows, which is the inbound, as well as the outbound flows, how many grams of CO2 per pallet it emits on a particular lane. So using that, for the current model output, we can determine what is the, as of today, current date, the emissions which are being released by the transporters in transporting Kissan jams. So you can see it is coming to a large number, but because it is in grams, so now it is 2.2 tons. Annually, the truck basically releases carbon dioxide as of today from the inbound transportation. Similarly, I will just multiply the demand with the configuration. As well as the carbon dioxide emissions to arrive at the figure for the Jaipur outbound. Again, I'll divide it by 10 to the power 7. I am getting 0.78 as the total outbound carbon dioxide emissions from Jaipur. I'll just paste the formula on the right and I'll get the total. So 2.84, remember this number, is the total outbound emissions, and total GHG emission, this is the most important number. Remember it is 5.04 tons annually. This is what Kissan Jams emits in this fictitious case. Now, this is how we factor in for climate change. Let's say we want to have a target of 5% reduction in carbon dioxide emissions in the upcoming fiscal year. So 5.04 is current. So what is we basically are trying to reduce 0.25 tons. So 4.79 tons is what our target is. So now how do we basically have the model accommodate this particular constraint? So you can just naturally think about it, because the weighted distance will reduce, because we want the carbon dioxide emissions to basically reduce. But in turn, because everything is a trade-off, currently it's the most optimal solution, the best solution. So because this constraint will make the model more constrained. So naturally the other costs will increase, which is the fixed and variable factory cost, if at all a feasible solution is possible. So we'll just go to the solver again and we'll add this particular constraint over here, which is the current constraint 5.04. The total GHG emission should be less than 4.79 in the new model output, and the solver will basically solve for that. So now we get a feasible solution, which is actually very good. And what we are seeing is 4.72 tons of GHG emission. Remember, it was 5.01. So we are basically reducing 0.3 tons. So that is the reduction. And what's the total supply chain cost is 4.69. Earlier it was 4.64. I've taken screenshots and we'll use it for comparison. Over here also you can see that 2.62 is the total transportation cost per road. Earlier it was 2.68, whereas the fixed and variable factory cost has increased in a proportionate way. So let me just show you the screenshot. You may just pause the video and have a glance at it if you want to compare in detail. I'll just navigate between both the images and you can see the difference for yourself. So as I've already explained to you from the cost parameter, how it has impacted, and it was natural when you think about it, how the weighted distance goes from 440 kilometers to 350 kilometers, which is a drastic improvement. But then the cost of the factory also increases because you are operating at a higher level for a particular factory. So you can see that the flows to Mangalore and Cuttack have changed in the revised optimal scenario. So this is the impact of having that extra constraint of GHG emissions. All the factories are activated, but in terms of the factory to distributor flows, if I just navigate, you can see that interchange, that Trichy, that particular service center, it was initially serviced by Cuttack, but now it is serviced by the Mangalore plant. So that has been changed. In terms of the factory production capacity also, Mangalore has been switched from the lower segment 10,000 to the higher segment 20,000. So there is naturally increasing fixed cost and variable cost associated with it. But then overall, while our cost has increased by roughly 5 lakh rupees, we are basically meeting our target of 5 lakh rupees of emission. I have also prepared a map-based current state and future state depiction. It gives a visual understanding of the flows and the impact of adding the GHG constraint. The farms are color-coded in red, factories are in green, and the distributors are in blue. The product flows are also color-coded accordingly. Naturally, you will see a bias for serving customers near to you and this current state map, but the significant agri-produce capacity differential between the Ranchi and Nasik farms has meant that Ranchi is serving more distant customers than it otherwise would have if both the farms' capacities were similar. This dichotomy is not that visible in the factory to distributor flows, which are more distance conscious due to their similar capacities. That being said, in the future state map, factoring in the GHG constraint, one can observe that the Trichy distributor will now be taken up by the Mangalore plant instead of the Cuttack plant previously. I hope you like this demonstration. Thank you.